I came to dance, 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 dance. Yeah. I hit the floor cause that's my plans, 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 plans. Yeah. I'm wearing all my favorite brands, 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 brands. Yeah. Give me some space for both my hands, 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 hands. Yeah, yeah, cause it goes on and on and on. And it goes on.
Hi.
Hi, may I help you?
Hi, my name is Grace, and I work at the Earl Hague Pharmacy.
I hit the floor cause that's my plans, 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 plans. Yeah.
Today, I'll be making 3 connections in the grade 12 chemistry course about the production and the function of pharmaceuticals. First, I'll be talking about the chemical equilibrium in the pharmaceuticals. Second, I'll be talking about the rate of reaction such as catalysts and other factors that will affect the rate of reaction. Lastly, I'll be talking about redox reaction occurring in the pharmaceuticals. Daily, we partake in duties that involve the knowledge of chemistry. We handle prescriptions that deal with chemical formulas, calculations, all the way to redox reaction. Connection 1. Equilibrium. In producing pharmaceutical products, maintaining an equilibrium is very important. Equilibrium is when the reactant and the product are in constant ratio. Therefore, the forward reaction and the reverse reaction occur at the same rate. Here is an equilibrium equation. Notice the double arrow between the reactants and the products, indicating reversible changes. Therefore, equilibrium can be approached from either direction. Here, there are 2 concentration versus time graph of hydrogen iodide. Looking at the first graph, the rate of the forward reaction decreases, where the rate of the reverse reaction increases. However, as time passes, equilibrium is reached and the macroscopic properties of the system are constant. In pharmaceuticals, to avoid the redeposit of the active solute in a saturated solution, maintaining equilibrium is crucial. This should never occur as the deposit may be detrimental to the health of the patient. Therefore, pharmacists must be able to calculate the amount or concentration of drug substances in each unit or dosage of a preparation at dispense time. Why calculations? Because they obtain theoretically 100% of the amount of each ingredient in a compound. To prevent this from occurring, equilibrium constants are calculated. Equilibrium constant is a ratio of the forward rate constant divided by the reverse rate constant. Simply, it is a ratio of products over reactant. Equilibrium constant is calculated using an ICE chart. Stands for initial, change, and equilibrium. ICE chart is used to keep track of the changing concentration in an equilibrium reaction. The first row has the initial concentration of acid, and since the reaction is initially undissociated, the concentration of conjugate base and hydronium is 0. The second row is a change occurring during the reaction. The third row is the sum of the first 2 rows and shows the final concentration of each. It can be seen from the table that at equilibrium, the concentration of hydrogen is X. To find X, the equilibrium constant must be specified. Not only is equilibrium constant calculated, but acid dissociation constant is also calculated. The reaction reacts with water because it's the most desirable solvent in the pharmaceuticals. Weak acids are used, and weak acids are the remainder of these strong acids. Aspirin made out of acetylsalicylic acid is an example of a weak acid. Base dissociation constant are for weak bases, and they are the remainder of these strong bases. For these 2 constants, the greater its value, the more acidic or basic the solution is. Also, these dissociation constants are important characteristics of drug molecules and provide a tool to anticipate some of the behaviors of the compound. So, by maintaining the equilibrium constant, the drug produced is now safe. Connection 2. Rate of reaction. Catalysts work by lowering the activation energy of a reaction so that a larger fraction of reactants can have a sufficient energy to react. This figure shows the activation energy for an uncatalyzed reaction and a catalyzed reaction. In pharmaceuticals, the variety of metal-bearing catalysts are used for facilitating hydrogenation and eliminating harmful exhaust emissions. The metal catalysts used include platinum and palladium. referred to as platinum group metals or 2-noble metals. These two catalysts are most frequently used because of their outstanding activity in reduction of a wide range of functional groups at low hydrogen pressure, and they have efficient recovery, which is important to control costs in manufacturing. They are usually supported on carbon carriers. Palladium catalyst is used for hydrotreatment such as hydrodeoxygenation, hydrodenitrogenation, and hydrodesulfurization. It is also used because reactions can take place at lower temperature with minimal side effects. These catalysts can be used in synthesis of vitamin A, vitamin B2, vitamin B6, dihydrostreptomycin, cortisone, and ephedrine. This is a chemical structure of dihydrostreptomycin. Increasing temperature increases the production efficiency and reduces its running time. In addition, the particle vibration is augmented and therefore its solubility and efficiency are amplified. Also, the reason for limiting temperature is to control the final concentration and to control the burnout. An example is acetonitrile. By using catalysts and increasing the temperature, the production of pharmaceuticals can be either a benefit or a disadvantage. Connection 3. Redox reaction. Redox reaction, also known as an oxidation-reduction reaction, is a reaction in which one reactant loses electrons and other reactant gains electrons. Oil rig. Oxidation is losing and reduction is gaining. This is an example of a reaction. This is its total ionic equation. By omitting the spectator ion, you obtain this net ionic equation. Zinc loses electrons whereas copper gains electrons. That was a simple redox reaction. The production of the pharmaceuticals involve exchange of electrons as they perform various of reactions. One example I came across was that recently there was an increase of pharmaceutical preparation containing fluoride ions. For example, when ions iron 2+, copper 2+, and fluoride are present in the environment of the reaction, the oxidation reduction potential will be changed in the iron 3+ or iron 2+, or copper 2+ or copper plus system, inducing a redox reaction. Furthermore, iron 2+ ions will be oxidized with copper 2+ ions to iron 3+. Thus, copper 2+ ions will be reduced to copper+, which will bound and precipitate. Also, these redox reactions, titration methods are used to determine the strength of the reductant and oxygen using a redox-sensitive indicator. For example, in pharmaceuticals, there are many indicators which are oxidized immediately after the last bead of reactant is consumed, producing a dramatic color change. Therefore, pharmaceuticals involve an extensive use of redox reactions. Oh, hello! I remember those grade 12 days. Good times, good times. Well, thank you so much for listening and joining me for an adventure in the pharmaceutical industry. Hope your trip was exciting and engaging. Thank you!